Okay, hello everyone. I hope you're all doing well. It's Monday morning here. Last lecture, I showed you the product rule. So let's start with a quick product rule application. We're looking at strings consisting of 75 symbols. And every symbol is either an uppercase letter or a digit. So how many of these strings are there? Okay, so remember, according to the product rule, we say, well, how can we obtain strings of this type? Well, we write them from left to right. So for the first symbol, we write either an uppercase letter or a digit. And there are 26 uppercase letters and there are 10 digits. So that means there are 36 choices for the first symbol. Once we have chosen the first symbol, we choose the second one. And again, there are 36 choices for the second symbol. And that doesn't depend on which symbol we chose for the first one. Okay, now after we have chosen symbols 1 and 2, we choose symbol number 3. And again, the number of ways to choose symbol number 3 is 36. And it doesn't depend on which symbols we chose for positions 1 and 2. Okay, so we do this 75 times. And then the total number of strings we can make of this type is equal to 36 times 36 times 36, and this 75 times. Okay, so the answer is 36 to the power 75. Okay, so let's change the question a little bit. We are still looking at strings of length 75. Every symbol must be an uppercase or a digit. But additionally, the string must contain at least one digit. Must have at least one digit. And how many are there of this type? Okay, so is there an easy way to count the strings? Length 75, every symbol uppercase digit, but the string must have at least one digit. Okay, so here in the 36 to the power 75, we have counted strings that do not have any digit. Okay, so the answer is definitely not 36 to the power 75. So how would you count these strings when you must write at least one digit? Okay, now a first idea would be to say, well, if there is at least one digit, that means the number of digits is exactly 1 or exactly 2 or exactly 3, etc., or exactly 75. So one idea would be, well, first we count the number of strings of this type that have exactly one digit. Then we count the number of strings of this type that have exactly 2 digits, then exactly 3 digits, etc. At the end, we count the number of strings of this type having exactly 75 digits. So then we get 75 different numbers and we add them all up and then we get the answer here. Okay, now that doesn't sound like a fun exercise to do. So if you think, right, you should think a little bit about it. Is there an easier way to count strings that have at least one digit? Okay, so the trick is to look at strings of this type that do not have this property. Yeah, so the property says there must be at least one digit. So let's look at the complement. So these are strings. The length is still 75, every symbol uppercase digit, and this condition is not true. Yeah, so it's not the case that there is at least one digit. That means we are looking at strings that don't have any digit and that only consist of uppercase letters. So these are 75 uppercase letters. And these strings are easy to count because this is a straightforward application of the product rule. So we want to write a string of length 75. Every symbol is an uppercase letter. Okay, for the first symbol, we have 26 choices. For the second symbol, 26. For the third symbol, 26. And for the last one, at position 75, we again have 26 choices. So that means there are 26 to the power 75. Many possible strings of length 75 where every symbol is an uppercase, a letter. Okay, so now what do we know? So here we said there are this many strings of length 75 where every symbol is an uppercase letter or a digit. There are this many strings that only consist of uppercase letters. So that means this is the number of strings that do not contain any digit. So how many are there that have at least one digit? Well, that is the total number of strings minus the number of strings for the complement. And that means the answer here is 36 to the power 75 minus 26 to the power 75. Okay, now of course this is a huge number. That's not a very nice number, but this is an easy way to count strings of length 75 that contains at least one digit. Okay, so the rule for this is called the complement rule. And the complement rule, in terms of a picture, so I'm drawing a Venn diagram. So here we have a set U, and here we have a set A. And so this here, these are elements that are in U, but not in A. And that I'm going to write as U minus A. So this is the set of all elements X in U that are not in A. Okay, so this is the complement of A. It should be clear that the number of elements in A plus the number of elements in the complement, so U minus A, that is equal to the number of elements in U. So the complement rule says the size of A equals the size of U minus the size of U minus A. Okay. Of course, this is a completely obvious rule, but it is still very useful. And when we were counting strings here of length 75 that have at least one digit, we were using this rule. Okay, so if we go back here, the set U here is the set of all strings of length 75, where every symbol is an uppercase letter or a digit. The set A, these are all strings in U that have at least one digit. And the set U minus A, that's the complement, is the set of all strings in U that have 0 digits, meaning every symbol is an uppercase letter. And the complement rule says the size of A, which is the number of elements, the number of strings we want to know, we want to count, is equal to the size of U. The size of U is there, minus the size of the complement. And the size of the complement is here. Okay, so the number of strings of length 75 that have at least one digit is equal to the size of U minus the size of the complement. Okay, so this is a very useful rule, and you typically apply this rule where you have a counting problem. You want to determine the size of a set A, and you don't know how to do it, or it is extremely painful to count it directly. In this case, it was painful because, as I said in the beginning, to count strings with at least one digit, we count strings that have exactly one digit, then we add to it the strings with exactly 2 digits, we add to it the strings that have exactly 3 digits, etc., etc. Okay, so then we have to add up 75 numbers. Okay, so we would like to determine the size of a set A. Either we don't know how to do it, or it is too much pain to do it, and then it is always helpful to look at the complement. Okay? And you typically apply this rule. Yeah? This is difficult to determine, but this is easy to determine, and this is easy to determine. Okay? So this is the complement rule. And now for the rest of today, today's lecture, I'm going to show you a few more rules that we will add to our toolbox. So the next one, this is again a completely obvious rule, but again it's useful. It's called the sum rule. In a picture, drawing a Venn diagram again. Suppose we have two sets A and B, and these sets are disjoint, which means the intersection of A and B is empty. Yeah, so there is no element that is both in A and in B. And we would like to determine the size of the union of A and B. Now, if you just look at the picture, since A and B do not share any elements, it should be obvious that the size of the union, remember the union, these are all elements that are in A or in B. If A and B are disjoint, then the size of the union is the size of A plus the size of B. Okay, so very simple rule, but it is useful. To give just a simple example, oops, let's go back here to strings here. I'm going to say, well, we are now looking at strings of length 75 or 76 or 77. Okay, so we want all strings of length 75 or 76 or 77. Every symbol must still be an uppercase letter or a digit. And we still have the requirement that the string contains at least one digit. So how many are there? Okay, so this is a typical case where you apply the sum rule. So here I explained it for two sets. If we have three sets, so I'm adding a set C here. And so we have three sets, A, B, and C, and they are pairwise disjoint. That means A and B do not intersect, A and C do not intersect, and B and C do not intersect. And I would like to know the size of the union of A, B, and C. So we want to know how many elements are there that are in A or in B or in C. Now, since there is no element that can be in two of these sets, the size of the union is just the sum of the sizes. So this is the size of A plus the size of B plus the size of C. Okay, so this is a sum rule for three sets. And of course, if we have four sets or if you have 100 sets, if you have 100 sets that are pairwise disjoint, then the size of the union is the sum of the sizes. Okay, so this sum rule you typically apply if you want to count the number of elements in a set, and you can divide this set into a number of pairwise disjoint subsets. So such that, so we divide the union into three pieces, and for every piece it is easy to count, or we already know how to count it. Okay, so let's go back here. How many strings are there of length 75 or 76 or 77? Every symbol, uppercase letter or a digit, and the string must have at least one digit. Okay, now remember the union of two sets corresponds to the logical OR. Okay, so by doing this, we can naturally divide these strings into three groups. Yeah, the first group, these are all the strings of length 75 having this property. The second group, these are all strings of length 76 having this property. The third group, these are all strings of length 77 having this property. And if you look at the fixed length, then it is easy. Or we know that we can use the complement rule to count them. Okay, so in this case here, the set A will be all strings of this type having length 75. The set B will be all strings of length 76. And the set C will be the set of all strings of length 77 that contain at least one digit. Okay, so if we take A union B union C, then we get exactly the strings that we want. And the sum rule says the total number of strings we can make, it is the sum of A plus the size of A plus size of B plus size of C. So what is the answer here? Okay, so the set A, these were all these strings having length 75. We just saw that. This is equal to 36 to the power 75. And then we subtract 26 to the power 75. So this is the size of A. Yeah, these are all strings of length 75 that have at least one digit. And how many such strings have length 76? Of course, we get the same expression, except the exponents become 76. So then we have 36 to the power 76 minus 26 to the power 76. So this is the size of B. And how many strings of length 77 are there of this type? And of course, that is the same expression, but now the exponent becomes 77. Okay, so this is a typical way where you use the sum rule. We want to count certain objects, and we can naturally divide these objects into different groups or different subsets, and these subsets are pairwise disjoint. So keep in mind, you can only apply the sum rule if A and B do not have elements in common, A and C do not have elements in common, and B and C do not have elements in common. If we divide these strings based on their length, so the set A, these are these ones here, and the set B are the strings of length 76, and it is clear that A and B do not share any string because they have different lengths. So we have divided these strings into 3 groups, and for every group, the length of the string is fixed, and then we use the complement rule to determine the size of one particular group. Okay, so the answer is this here. So this is the sum rule. Okay, so the next rule is, now if we look again here, so the sum rule only applies if the sets are pairwise disjoint. So what happens if we want to, let's say we only have 2 sets, A and B, and they share elements, and we still want to count the size of the union. So let's see, what do we get there? Okay, I'm going to erase this. Okay, so as before, I recommend that you write down these rules on a piece of paper, just like the product rule, and keep this piece of paper next to you. Okay, so let's see. So we have 2 sets, A and B. And now there are elements that are both in A and in B. And we want to determine the size of the union. A and B are finite sets. Their intersection is non-empty, and we want to know how many elements are there in the union. Okay, now as we saw, for the sum rule, if A and B are disjoint, then it is equal to the size of A plus the size of B. So let's just start with this. Okay, so this is not a final answer yet, but at least we start like this here. So we start with the size of A plus the size of B. And now look in this Venn diagram here. If you have an element of A, it can be here. That means it's in A but not in B. Or it can be there, which means it is both in A and in B. So here we have the size of A. That means every element that is in A but not in B has been counted once. every element that is both in A and B has been counted once. Okay, so this is the term, the size of A. Then we said, well, we add the size of B. Now, an element of B, it can be here, that means it's in B but not in A, or it can be there. It is both in B and A. So here in the size of B, we have counted elements here once, and elements that are in A and in B, we counted them again. Okay, so what we have counted here, we have counted these elements once, we have counted these elements once, but elements that are both in A and B, we have counted twice. So in order to get a final answer, the size of the union, we're going to subtract the size of A intersected with B. Okay, so this was union, elements that are in A are in B. This is the intersection. These are elements that are in A and in B. Okay, so here we subtract elements that are in the intersection of A and B. So in this picture here, we get a minus sign. Okay, so there is one plus sign because of the size of A, there is another plus sign because of the size of B, and there is a minus sign because of A intersected B. And if we now look here in the picture, the intersection we have counted twice with a plus sign, and we have counted it once with a minus sign. Yeah, so overall, we have counted elements in A intersected B exactly once. Okay, so this means the size of the union is the size of A plus the size of B minus the size of A intersected B. Okay, now this is again a very simple but useful rule, and this is called inclusion-exclusion. Okay, so why is this called inclusion-exclusion? It says, well, we want to determine the size of the union. So first we include the two sets, but from the picture, by doing this, we overcount. So we include the sets and then we exclude the intersection. So this is called inclusion-exclusion. It's a very simple rule, but it's very useful. Okay, so let's do a quick example. We're going to count bit strings. Of length 75. So you write down 75 bits. So it is a sequence consisting of 75 many zeros and ones. And we want strings that start with 10101 or end with 1100. Okay, so we're asking how many bit strings are there. They start with this or end with this. So in a picture, the length is 75. And they start with 10101 or 1100. And again, the length is 75. Okay, so how many bit strings are there? Okay, so the first idea is, well, we want to count strings of this type, where now we want to count strings, everything being of this type or of this type. So so this is naturally divided into two groups. So this is the first group. This would be the set A here. This would be the set A, and this would be the set B. And so A is a set of all bit strings of length 75 that start with 10101. B is a set of all strings of length, bit strings of length 75 that end with 1100. And because of the OR here, we are asking for the size of A union B. Yeah, so this is what we want to know. And so A union B, these are all strings that are in A, that means of this type, or they are in B, that means they are in this type. Okay, now notice we cannot just apply the sum rule because A and B, they share strings, right? So if you have a bit string that starts with 10101 and ends with 1100, then it is both in A and in B. Okay, so for this example, we have to use the inclusion-exclusion formula. Okay, so the size of the union, inclusion-exclusion says, well, we take the size of A, we add to it the size of B, and we subtract A intercepted B. Okay, and we will see in a moment. So here we have three terms, and each of these terms is easy to determine. So let's see, how can we do this? So how many strings are there in the set A? A is a set of all bit strings of length 75, where the first 5 bits have been fixed. So in order to obtain a string in the set A, we have to choose the last 70 bits. Yeah? And this is a simple application of the product rule, because the size of A is equal to the number of bit strings of length 70. Okay, so we have to write down 70 bits. For the first bit, 2 choices, next bit, 2 choices, 2 choices, etc. So the size of A is 2 to the power 70. So these are all bit strings of length 75, for which the first 5 bits have been fixed. What about the size of the set B? Well, for B, the last 4 bits have been fixed, and we have to choose 71 bits. Okay, so the number of ways to do this is 2 to the power 71. Because we have 75 bits, and the last 4 of them, they must be 1100, so we really have to choose 71 bits. So now I have to subtract A intersected B. So these are all the strings that are in A and in B. Now if they are in A, that means the first 5 bits have been fixed. If they are in B, that means the last 4 bits have been fixed. So that means if you are in A intersected B, the first 5 bits are fixed, the last 4 bits are fixed. That means overall 9 bits have been fixed, and we have to choose the remaining bits. And how many are there? That's 75 minus 9, which is 66. So the size of A intersected B is equal to 2 to the power 66. And again, the reason is because we have fixed 5 bits and the first 5 and the last 4. So overall, we have fixed 9 bits. So we have to choose 66 bits. Okay, so the number of bit strings of length 75 that start with 10101 or end with 1100 is equal to this use number here. Okay, so this is a simple example where you use the principle of inclusion-exclusion. We want to know the size of the union. We include both sets A and B, and then we exclude the intersection of A and B. Yeah, and of course, you typically apply this principle of inclusion-exclusion when this is difficult to count, and these 3 terms here are easy to count. Okay, so this is inclusion-exclusion for 2 sets. First, notice that this formula here that expresses the size of A union B, it is also true if the intersection of A and B is empty. So if A and B do not share elements, then the size of A intersected B is equal to 0. So if A and B are disjoint, then this formula here is really the sum rule. And again, if A and B do not share elements, then this is 0. Okay, so this is inclusion-exclusion for 2 sets. Now, we can do the same thing for 3 sets. So let's do this. So I'm going to draw a Venn diagram again. We're having 3 sets. A, B, and C. And we want to know the size of A union B union C. Okay, so we have 3 finite sets, A, B, and C. This is the union of A, B, and C, so these are all elements that are in A or in B or in C. Okay, so we're going to use the same principle as we did for 2 sets. So let's start with the size of A plus the size of B plus the size of C. Okay, so we want the size of the union, and we start by including A, B, and C. Okay, so now we go back to the Venn diagram here. Here we have the size of A. Now, elements of A, they can be of 4 different types. Some elements are here. That means they are only in A. Some elements are here. That means they are in A and in B, but not in C. Some are here. That means they are in A and in C, but not in B. And some of them are there. That means they are in all 3. So if we just look at the size of A, then we have counted elements here. We have counted elements here. We have counted these, and we have counted these. Okay, so the term here, the size of A, elements here have been counted once with a plus sign. These have been counted once, counted once, counted once. Then we get the size of B. And again, there are 4 different types of elements in B. So elements that are only in B, not in A and not in C, they have been counted once. Elements that are in A and in B, but not in C, have been counted once. These elements here, they are in B and in C, but not in A, they have been counted once. And elements that are in all three, they have been counted once again. Okay? So this is when we add the size of B. Now we add the size of C, and I hope you see what is happening here. So elements of C, they can be only in C. They can be here. That means they are in C and in A, but not in B. They can be here, meaning they are in B and in C, but not in A, and they can be here. Okay, so if we look at the size, the sum of the sizes of A, B, and C, these elements have been counted once. These have been counted once, counted once. These have been counted twice. These have been counted twice, counted twice. These have been counted 3 times. Okay, so far we have included the sizes of A, B, and C. Now for 2 sets, we said, well, we exclude the intersection of 2 sets. So let's do that here. So let's subtract now the size of the intersection of A and B. Okay, so let's go back to the Venn diagram. The intersection of A and B is this part here. Yeah, and the intersection of A and B consists of 2 different groups. There are elements here. They are in A and in B, but not in C. And there are elements here that are in all 3 sets. So if I subtract the intersection of A and B, then we get a minus here and we get a minus there. So elements here now, they have 2 plus signs and 1 minus sign. So these are elements that are in A and in B, but not in C. 1 plus comes from here, 1 plus comes from here, and the minus comes from there. So we have subtracted the intersection of A and B. So let's do the same thing with the intersection of A and C. A intersected C. In the picture, A intersected C is here. So we subtract these elements and we subtract these elements here. Okay, and let's also subtract the intersection of B and C. And if we go back to the Venn diagram, B intersected C, that means they are here. So that means element here. We have subtracted, and elements here we have subtracted. Okay, so we are not done yet. We're getting close. So what have we done so far? We want the size of the union of A, B, and C. We include A, B, and C, and then we exclude the pairwise intersections. We exclude A intersected B, we exclude A intersected C, we exclude B intersected C. Now, if we look in the Venn diagram, then we can see how far we are now. Elements here, so they are only in A, they have been counted exactly once. Elements in B have been counted exactly once. Elements that are only in C have been counted exactly once. If we look at elements in this part of the diagram, so these are elements that are in A and in B, but not in C. They have been counted twice with a plus sign and once with a minus sign. So that means overall we have counted elements here exactly once. So this is good. This is what we're aiming for. If we look at elements here, So they are in A and in C, but not in B. They have been counted twice with a plus sign and once with a minus sign. So that means overall they have been counted exactly once. This is also perfect. Elements here, they are in B and in C, but not in A. Twice with a plus sign, once with a minus sign. Overall, we have counted them exactly once. But now look here. So these are all elements that are in A and in B and in C. They have been counted 3 times with a plus sign and 3 times with a minus sign. So on the right-hand side here, we did not count elements that are in A, B, and C. So how do we get the final answer? Well, we are just going to add the intersection of A, B, and C. So these are all elements that are in A and in B and in C. And if we go back to the diagram here, so what do we, this is exactly the elements we didn't count yet. So we get another plus here. And now you see, if you look at the intersection of A, B, and C, there are 3 minus signs and there are 4 plus signs. So that means overall we have counted elements in the intersection of all sets exactly once. So the expression for A union B union C is the right-hand side here. Okay, so we have a union of 3 sets. We start by including the sets themselves, then we exclude the pairwise intersection, and then at the end we include the intersection of all 3 sets. And so this is inclusion, exclusion for 3 sets. Now I hope you can imagine that we can also do this for 4 sets. I'm not going to draw a picture because that becomes a mess. If you have 4 sets, then the size of the union, you take, well, first we include the sets themselves, then we exclude the pairwise intersections, then we include the triple intersections, and then at the end we exclude the intersection of all 4. Okay, so of course you can also do this for 5 sets and 6 sets. The idea is exactly the same. But in this course, we are only going to use it for up to 3 sets. Okay, so let's look at a simple example. So let's extend. We are again looking at bit strings of length 75. They should still start with 10101 or end with 1100, or they have 101 at positions 13, 14, 15. Okay, so I'm going to add this to the picture here. So we have to write 75 bits. And what did I say here? 101. So these are positions 13. This is position 1 here. This is position 75. 13, 14, 15. Okay, so we want to count the bit strings of length 75 such that the first 5 bits are equal to this, or the last 4 bits are equal to this, Or if you look at positions 13, 14, 15, you must see 1, 0, 1. Okay, so this is strings of this type, or of this type, or of this type. And remember, or corresponds to a union. So we can again naturally split strings of this type into 3 groups. The set A is the same as we had earlier on. We write it here and make some space. This is the set A, this is the set B, and this is the set C. And we are really asking for the size of the union of A, B, and C. Okay, so we have 3 sets, A, B, and C, and we want to determine the size of the union. As for the previous example, where we only had A and B, observe that A and B, they share strings, A and C share strings, and B and C share strings. Okay, so we cannot just use the sum rule, because the sum rule can only be applied if the strings are pairwise disjoint. Okay, so the formula for the size of the union is here. So we just go through the right-hand side, and then for every term you see there, we're going to determine the size. So what is the size of A union B union C? Okay, so inclusion-exclusion says we start with the size of A. How many elements are there in A? We saw that already. So we have bit strings of length 75. The first 5 bits are fixed. So we have to specify 70 bits. So the size of A is 2 to the power 7. Then we get the size of B. We saw that already. If you are in B, then the last 4 bits have been fixed. So we have to choose 71 bits. Get 2 to the 71. Next, we get the size of C. How many strings are there in the set C? Well, if a string is in C, 3 bits are fixed. So we have to choose the other 72. So we get 2 to the 72. That is C. Now we have to subtract A intersected B. So what is the size of A intersected B? You are in A and in B, so the first 5 bits are fixed, the last 4 bits are fixed, so overall 9 bits are fixed. We have to choose 66. So that is 2 to the 66. Now we have to subtract A intersected C. So strings of this type and are also of this type. A says the first 5 bits are fixed. C says the bits at position 13, 14, 15 are fixed. So if you are in A and in C, then we have fixed 8 bits. So if you are in A and in C, then we have to choose 75 minus 8, which is 67. I hope. Is that 67 plus 8? Yes, that's 75. So the intersection of A and C, so we are in A and in C, 5 bits are fixed, and these 3 bits are fixed, so we have to choose 67 bits. The next term is B intersected C, so the last 4 bits are fixed, and these 3 bits are fixed. So if you are in B and in C, then 7 bits are fixed. So we have to choose 68. So we subtract 2 to the power 68. And finally, we have to add all strings that are in A and in B and in C. Okay, so if you are in A and B and C, that means the total number of bits that are fixed, it is 5 plus 4, which is 9, plus 3, which is equal to 12. So the number of bits we have to choose is 75 minus 12, which is 63. Okay, so the total number of bit strings of length 75 that start with 10101 or end with 110 or have 101 at positions 13, 14, 15 is equal to this number here. Okay, so this is a simple way to illustrate inclusion, exclusion. Okay, so always inclusion, exclusion is always used if you want to determine certain objects that have property 1 or property 2 or property 3. You know? And you use it in case there are objects that can have multiple properties at the same time. Okay, so now we have seen different rules. We have the product rule, that is sort of the main rule. We have seen the complement rule. The complement rule says if you want to count objects that have a certain property, then often it is easier to count the objects that do not have the property. We have seen the sum rule. If you have disjoint sets, pairwise disjoint sets, then the size of the union is the sum of the sizes. If you have sets that are not necessarily pairwise disjoint, then to determine the size of the union, you use inclusion, exclusion. Okay, and keep in mind, if you don't remember the formula here, it is very easy to derive the formula by drawing the picture and then going through it the way I derived it here. Okay, as a last remark here regarding inclusion, exclusion, if the sets A, B, and C happen to be pairwise disjoint, then this formula here is still true. Because in that case, so if A, B, and C do not, they are pairwise disjoint, so any two subsets have an empty intersection, then this term is 0, this term is 0, this term is 0, and this term is equal to 0. So in that case, we just get the sum rule back. Okay, so this is inclusion, exclusion. Okay, so as before, write these rules on a piece of paper. And when you do the assignment questions, often the first question you ask yourself is, if I want to do the assignment question, which of the rules do I apply? Okay, the next topic that we need is the notion of a permutation of a set, permutation of a finite set. This is an ordered sequence in which you see every element of S exactly once. I'll give you an example in a moment. Each element of S appears exactly once. Okay, so for example, if S is the set ABC, then to obtain a permutation of S, you have to write the symbols A, B, and C in some order. So the different permutations are, well, you can write ABC, or you can write ACB. Okay, so this is a different from this. So you write down every element of S exactly once, and then you specify the order, the left to right order. Other permutations are B, A, C, B, C, A, then there is C, A, B, and there is C, B, A. Okay, so these are all possible permutations of the set A, B, C. And so these are the different ways in which you can order these elements here. And how many are there? It is 1, 2, 3, 4, 5, 6. Okay, so now in general, if your set has size n, how many permutations are there? Can we count this? So if n is equal to 3, then the number of permutations is equal to 6. So how would we count the permutations of a set of size n? Okay, now remember, a permutation, it is an ordered sequence where you see every element exactly once. So we could write permutations from left to right. Yeah, and this is exactly what the product rule framework does. Okay, so we could write the permutation from left to right. So we write the first symbol, then the second symbol, and then the third symbol, etc. And then in every step we can ask, well, how many choices are there? Okay, so if we write a permutation of a set of size n, so this has length n here. How many ways are there to do that? Well, if we write the permutation from left to right, we have to choose the element that goes first. And in this example, when n equals 3, the first symbol can be A or B or C. Yeah, we can pick any one that we like. So in general, if the set has size n, for the first symbol, the number of choices is equal to n. And so in this case, we can choose an A, or we can choose a B to go first, or we can choose a C to go first. Okay, now suppose we have already chosen one. So we have picked one element in S, which goes at position 1. Then if we go to position 2, we have to choose an element there. We are not allowed to choose the element that we chose there. So the number of choices for the second position is 1 less, because this element has been fixed already and we cannot choose it again. So we have n minus 1 choices for the second one. For example, if S has size 3, suppose for the first position we chose a B, then in the second position we either write an A or we write a C. Yeah. If we decided to go for the A in the first position, then the second position is a B or a C. Yeah. And remember, from the product rule, we needed the fact that when you do task number 2, which means choose the element at position 2, the number of ways to do that does not depend on the way we did task 1. Yeah, it is the actual choices are different. If we start with a B, we can choose A or C. If we start with an A, for the next symbol, we can choose a B or a C. But the number of ways to choose the second is always 2. Yeah, and in general, the number of ways to choose the second symbol is 1 less than the size of S. Okay, so now we go to task number 3. That means choose an element here that goes to position 3. How many choices are there? Well, we can pick any element except the element we chose here and except the element we chose there. So there are n-2 choices here. Yeah. And again, the number of choices does not depend on which choice we made for position 1 and which choice we made for position 2. Now, of course, this continues. If we have chosen the first 3 elements in the permutation, then we have n-3 choices for the element at position 4, because we are not allowed to pick this one, not allowed to pick this one, not allowed to pick this one. And of course, this continues. We have n-1, -2, -3. The next one is n-4 when we reach here. So we are almost done. How many choices are there? Well, when we choose this value here, we have already chosen n-2 elements. So there are only 2 elements left to choose from. So there are 2 ways to do that. And then finally, we have to choose the final symbol in the permutation. And of course, there is only 1 way to choose that. Because if we reach to the point where we have to choose the final element, that means we have already determined the first n-1 elements, and there is only 1 element left. Okay, so this is exactly what we need in order to apply the product rule. The product rule says the total number of permutations is equal to n times n-1 times n-2 times n-3 all the way down times 2 times 1. And this is equal to n factorial. So if you have a sequence, a set of n elements, and you want to choose an order for them, there are n factorial many ways to do it. Okay, when n is equal to 3, then we get 3 factorial, which is 1 times 2 times 3, and that is indeed equal to 6. Okay, so this is the notion of a permutation of a set. And keep in mind, when you talk about permutations, there is an order. Okay, so the next thing that we need, let's say we have a set of size 5. A, B, C, D, E. And now we are asking how many subsets are there of size 3? Okay, so we want to choose subsets of size 3. Notice here I'm talking about subsets, and in a set the order of the elements doesn't matter. Okay, so in the case of 5 elements, we could just write them all down. So let's see. So I'm going to write down all subsets of size 3. Okay, so we can take A, B, C. You can take A, B, D. Take A, B, E. So we have A, B, C, A, B, D, A, B, E. Then we do A, C, D, A, C, E, and then we do A, D, E. Okay, so now we have all subsets of size 3 that contain A. B, D, E. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is one missing, which is C, D, E. Okay, so here is a list of all subsets of size 3. Before 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the answer is 10. Okay, so there are 10 subsets of size 3. Okay, so here we determine the answer just by listing them all. But if I give you a set of size 1,000,000, and now I ask how many subsets are there of size 100, right? Then you don't want to write them all down. Okay, so we're going to look at the question, if you have a finite set, let's say of size n, and now you want to determine the number of subsets of some size, let's say k. Is there a simple formula for this? And of course, the answer is yes. Let me erase this. Okay, so in general, if we have a set of size n, and we want to know how many subsets are there of size k. We're going to use this symbol here. So this here is equal to the number of subsets of size k. Okay, so this is the definition of this symbol. And this is pronounced as n choose k. And this is called a binomial coefficient. Okay, so this is just a symbol, and this is a number, and which number is it? Well, you have, it is pronounced n choose k. You have a set of this size, and you want to count the subsets of this size. So you have n elements, and out of these n elements, you choose k. And keep in mind, we are talking about sets, so the order doesn't matter. Yes, n choose k is equal to the number of subsets of size k. So if we go here, so what is 5 choose 3? 5 choose 3. It means we have a set of size 5 and we count subsets of size 3. And we just saw that this is equal to 10. As an exercise, you can determine 5 choose 2. So 5 choose 2 means you have a set of size 5 and you count subsets of size 2. Yeah. And if you, so you can write them all down explicitly, and then you will see that the answer is again 10. So 5 choose 3 equals 10, and 5 choose 2 is also equal to 10. And you see these are equal, and that's not a coincidence. There is in a few lectures, I will show you a very easy explanation why this number must be equal to this number. Okay, so if we go back here, yeah, so n choose k, you have a set of this size, and we count subset of this size, yeah? So what would n choose 1 be? N choose 1, right? We have a set of size n, and we want to choose a subset of size 1. In this case, the set has size 5, and how many subsets are there of size 1? And the answer, of course, in this case is 5. Right? A subset of size 1, either you pick A, or B, or C, or D, or E. And in general, n choose 1 is equal to n. What is n choose n? Yeah. We have a set of size n, and we want to choose a subset of size n. If we go back here to this example where the set has size 5, we would get 5 choose 5. So we want to take a subset of size 5. And how many are there? Well, of course, there's only one. And there is only one subset of size 5, namely the entire set. And so n choose n will be equal to 1. Now what is n choose 0? We have a set of size n, and we want to count the subsets of size 0. Okay. In the example here, the set has size 5. And how many subsets are there of size 0? Well, there is only one subset of size 0, namely the empty set. Yeah, so there is only one subset of size 0 of this set. Yeah, so n choose 0 is equal to 1. Yeah, we have a set of size n, and we want to choose a subset of size 0. And the number of ways to do this is 1. So here we have 5 choose 3. So what is 75 choose 77? What would this be? We have a set of size 75, and we want to choose a subset of size 77. Okay, now if you have a set of size 75, then every subset has size less than or equal to 75. Okay, so here the answer is equal to 0. Yes, because it is not possible to choose a subset of size 77 out of a set of size 75. One more example. What would be 0 choose 0? So we have a set of size 0, which means it is the empty set. and we want to choose a subset of size 0. Okay, now keep in mind the empty set is a subset of the empty set. Okay, so here we have a set of size 0, which we have an empty set, and we want to choose a subset of size 0, which we have to choose the empty set. And the empty set has only one subset of size 0, namely the empty set. So 0 choose 0 equals 1. Okay, so here we see the value of n choose k for different values of k. So n choose 1, that's an easy one. N choose n is easy. N choose 0 is easy. N choose k, where the k is bigger than n, that's equal to 0. That's also easy. We determine 5 choose 3 by making a list of all subsets of size 3, which was a bit of a pain. You can make a list of all subsets of size 2. That shows that 5 choose 2 is 2. So our goal now is to come up with a general formula for n choose k. So the claim will be that if k is at least 0 and at most n, then n choose k. So again, this is the, you have a set of size n and you count the subset of size k. This is equal to n factorial divided by k factorial divided by n minus k factorial. This is the claim. So as a quick check, let's verify that 5 choose 3 for this formula, that we really get 10. So 5 choose 3. This is, okay, so n choose k, we take n factorial, so we get 5 factorial. Then we divide by k factorial, which becomes 3 factorial. And then we divide by n minus k, that's top minus bottom, that's 5 minus 3. So that is 2 factorial. So let's write this out. 5 factorial is 1 times 2 times 3 times 4 times 5. 3 factorial is 1 times 2 times 3. 2 factorial is 1 times 2. Okay, so 5 choose 3. The right-hand side is equal to this. Now we have a 1 here, they cancel, the 2's cancel, the 3 cancels. The 4 over 2 becomes 2. 2 times 5, and yes, we do get 10. Okay, so the formula here, the expression for the binomial coefficient n choose k, is equal to that, and at least this here verifies that this is true if n equals 5 and k equals 3. Okay, so this is the end of lecture number 3. In the next lecture, I will start by showing you why n choose k is equal to this fraction. Okay, so as always, write this down on a piece of paper. Basically this part here, and keep it next to you. This here, n choose k, this is how you pronounce it. We have a set of this size, and we want to count subsets of this size. And the total number of subset is equal to this number here. Okay, thank you then, and see you next time.